You know, in electrical engineering, we're pretty much obsessed with efficiency. So what if I told you that you could build a transformer that's smaller, lighter, and more efficient just by removing a major part? I know, it sounds like it shouldn't work, but that's the absolute genius behind the autotransformer. Today, we're going to unpack this brilliantly simple device that really does more with less. So here's our game plan. We'll kick things off with a quick look at the classic transformer. Then we'll see how the autotransformer uses its clever single winding trick. We'll get into how it works, check out the math, put it head to head with a regular transformer, and finally, see where these things are being used out in the wild. All right, to really appreciate just how clever the autotransformer is, we've got to start with a quick refresher on the classic design it improved on, the good old two-winding transformer. Okay, the key thing to grab from this definition is that phrase electrically isolated. All that means is there is no direct wire connecting the input circuit, the primary, and the output circuit, the secondary. They're completely separate. And that separation is a huge deal for safety and design. And this diagram shows it perfectly. See, you've got the primary winding on the left, secondary on the right. Current comes into the primary, creates a magnetic field in that iron core, and that field induces a totally new voltage on the secondary side. Power literally jumps the gap using only magnetism. Now, that two-winding design is a workhorse. It's been around for over a century, but engineers are always asking, how can we make this better? How can we make it more efficient, cheaper? And that leads to a pretty revolutionary what-if moment. No, really, just think about that for a second. What if you could just get rid of an entire coil of that expensive copper wire? That one question is the little spark that led to the autotransformer. It's a design born from that simple but powerful idea of doing more with less.
And here it is, the simple, elegant answer. An autotransformer doesn't bother with a separate primary and secondary. Instead, it has one continuous winding, and a part of that winding is literally shared by both the input and the output circuits. It is an incredibly clever idea.
This side-by-side really makes it click, doesn't it? On the left, you've got your standard two-coil setup. On the right, the streamlined autotransformer. You can immediately see how much simpler it is. You're using less copper, which means for the same power, it's going to be smaller, lighter, and cheaper to make. This simple physical difference is the reason for all of its advantages.
So the big question is, how on earth does this one coil do the job of two? It's not magic, I promise. It's actually a very smart combination of two different physical principles working together perfectly.
Okay, let's break this single coil down. The whole thing acts as the primary winding, but it helps to think of it in two parts. The top section, which is only part of the primary circuit, we call that the series winding. The bottom section, now this is the key, is connected to both the input and the output. That's the common winding. And that shared section is really the heart and soul of the whole thing. And here is the secret sauce. An autotransformer moves power in two ways at the same time. Some of the power is transferred inductively. That's the normal magnetic way we just saw. But a whole chunk of the power is also transferred conductively, flowing directly through that shared common wire. It's like an electrical shortcut. And that direct connection is what makes it so incredibly efficient. But it's also its biggest trade-off, which we'll get to in just a minute. Okay, so we've got the concept down. Now let's look at the elegant math that makes it all work. And these formulas aren't just numbers on a page. They show you exactly how the voltage and current get shared and changed inside that single coil. Everything kicks off with the turns ratio, which we'll just call A. But it's defined a little differently here. Instead of comparing two separate coils, we're comparing the number of turns in the series part to the number of turns in the common part. This single ratio is the key that unlocks how all the voltages and currents are related. And this makes total sense when you just look at the diagram. The input voltage, V1, is applied across the whole winding from top to bottom. So it has to be equal to the voltage across the series part, Vs, plus the voltage across the common part, Vc. It's really just simple addition. Right, now let's connect it all together. Remember that the output voltage, VL, is just the voltage across that common section, Vc. So when we combine our turns ratio A with a simple addition from before, we get this nice clean formula. The final output voltage is just the input voltage divided by 1 plus A. That's pretty much the core formula for a step-down autotransformer. And guess what? The exact same beautiful logic applies to the current. The total current going out to the load, IL, is just the sum of the current coming down from the series section and the current that was already in the common section. And again, using our ratio A, we find that the load current is equal to 1 plus A times the series current. The math just beautifully confirms how everything is shared. So we have established that the autotransformer is smaller, lighter, and more efficient. But as any engineer will tell you, there's no such thing as a free lunch. So let's put these two designs head to head and really see the trade-offs. This table lays it all out pretty clearly. The autotransformer wins on almost everything. It's smaller, lighter, more efficient, and costs less. It even has better voltage regulation, which just means its output voltage stays more stable as the load changes. But there is that one huge difference: isolation. A conventional transformer isolates the two circuits. An autotransformer does not. That direct physical connection means a problem on one side can easily travel to the other.
So given that really important trade-off, where does it actually make sense to use an autotransformer? Let's take a look at the applications where its unique strengths can really shine.
You'll find them at the very heart of our electrical grid, in huge power distribution systems where you're moving massive amounts of energy across the country. Even a tiny gain in efficiency saves an enormous amount of money and energy. In these big systems, engineers know all about the lack of isolation, and they simply design around it. And diving a little deeper, here are some perfect use cases. They're great for linking power grids that run at slightly different high voltages. They're used to give a small voltage boost on long power lines to make up for any drop. They're also used as starters for massive industrial motors to reduce that big surge of current at startup. You'll even find them powering industrial furnaces.
So here's the most important takeaway. The benefits of an autotransformer are biggest when the input and output voltages are pretty close to each other, when that voltage ratio is near 1-to-1. And, just as importantly, you only use them in situations where that direct electrical connection is safe and acceptable.
And that leaves us with a fundamental question that engineers face all the time. Do you go for the raw efficiency, the smaller size, and lower cost of the autotransformer? Or is the total safety and circuit separation that you get from a conventional transformer just something you can't compromise on? The answer, as we've seen, really depends on what you're trying to do.
Namaste. Thanks for watching. Stay tuned for more.